Yes, I do. Okay,
All
so
right.
great.
The picture of Lewis.
Yes. Okay, so great. So to introduce Markus Müller, who's based at Equality in Vienna. And thanks very much. Yeah, take it away.
Yeah, so thanks for having me, Dan, Gerardo, and Tao. It's great to be here virtually. Let me say two things before I begin. First, I apologize in advance if I cough and have to stop sometimes. It's just a bad cold. And the second thing, I want to use this opportunity, I thought just to thank Luis Massanes. So here I'm talking about deriving quantum theory from simple principles, and this has been worked with several colleagues. But a lot of it has been done with Luis, and Luis is really the mastermind behind many of the ideas that I'm talking about. So special thanks to Luis.
Thank you, Markus.
Yes, yeah. Just, you know, he's behind many of the ideas that I'm talking about today without mentioning him all the time when it comes up. So I thought I mentioned it on the first slide. Now here's an overview of my talk. I will begin with a little tutorial. For those of you who haven't seen generalized probabilistic theories before, I will talk briefly about how could physics be more general than quantum. How could we have probability theory that's not even quantum? Given then that we have that kind of framework, we can talk about deriving quantum theory from simple principles. And in the second part, I will give one example derivation. There are many others, but I'll just give one of them. The third part will be some kind of detective story, the quest for beautiful theories of higher order interference. And I will tell you whether that succeeded or not in a minute. And in the last part, I will touch on something that you can see very nicely when you take this general probabilistic theory framework into account. Namely, you can see in some cases that the structures of space-time and quantum theory are related to each other in some nice ways. Okay, so let me begin with the first part. How could physics be more general than quantum? What do you mean by that? So let me tell you one example. One example how it could be more general is in the context of a Bell experiment. This is a very schematic sketch of a Bell experiment. So you think of Alice and Bob in their local laboratories, and they are very far away, so they are space-like separated, and they share some resource that somebody transported to their labs beforehand. And now what Alice can do is she can input something to her laboratory, perhaps to a box that she has in her lab. The input will be called X, and then she will receive an outcome A. Bob inputs something called Y, and Bob will receive an outcome B. Now, if you imagine that they can repeat this experiment many times, and they can determine the conditional probabilities of the outcomes A and B, given their inputs or settings X and Y. So how would we formalize this in classical physics or classical probability theory? Well, you'd say if we have this kind of causal structure, say in the sense of Pearl or so, then we would have some variable lambda, sometimes called hidden variable. Think of it as some shared randomness, some correlation that has been established beforehand. And then we have local response function for Alice. So Alice's probability that she gets outcome A given her input X and the value of lambda. And then something independent, the same for Bob. And all in all, we get the probabilistic mixture of all those things. And this gives us the probability table. Quantum physics, we have more general objects. We can think of a quantum state, for example, an entangled state that's shared between Alice and Bob. And then Alice and Bob perform measurements determined by these operators, EXA and FYB. And then we just have the usual trace rule or Born rule to determine the probabilities and correlations. Now, we all know that this is really interesting because quantum theory really admits more general probability tables, correlation tables than classical physics would, because quantum theory can violate Bell inequalities. Now, before saying more about that, let me mention, however, one aspect in which classical and quantum are similar. So in both cases, both theories satisfy the no signaling conditions. So what this means, for example, that if Alice looks at the probability of her outcome A, given her input X and given Bob's input Y, then this turns out to be independent of Y. So the local probabilities in one laboratory are independent of the settings in the other laboratory. And that's for sure important, because if that was violated, then Alice and Bob could instantaneously signal, and they could send information faster than light, basically. But this is excluded in classical and in quantum physics. Both satisfy the no signaling conditions. Now, here's an example of a Bell inequality, the Bell CH-SH inequality, Clauser, Horn, Shimony, Holt. So what you can do is you take your probability table and you compute these correlators CAB. So that's like the expectation values of the products of the outcomes. If you think that the outcomes are +1 or -1, then you can multiply them together and get these correlators. Classical physics, you find that if you compute this number here on the left-hand side, this is always upper bounded by 2. But we know that in quantum theory, you can, for example, with singlet states, violate it, and you can get a larger value up to 2 square root of 2. Now, in the 90s, Popescu and Rohrlich were famously asking a question. They were saying, hey, we know that we live in relativistic space-time, so there should not be signaling. Given that, perhaps is quantum theory the most general thing we can have? Could that be? So what they asked is, are the quantum correlations, are these the most general correlations that would satisfy the no signaling principle? And the surprising answer turns out to be no. So there are correlations now called Popescu-Rohrlich correlations, already due to Zirelson, that are given in the box here. So what are they saying? They say in the last line, it says, if Alice and Bob choose as inputs or as settings 1, both of them, then they get either outcomes +1 and -1 or -1 and +1 with 50% probability. So they get anti-correlated outcomes. But in all other 3 cases, and that's the first line, they get perfectly correlated outcomes. Now you can see that this thing can check that this satisfies the no signaling conditions. But if you compute the CHSH value, it gives you a larger value of actually 4. And 4 is more than quantum theory can allow. So in this sense, these PR boxes in some sense describe alternative physics that's not possible in quantum physics, but that we could think of having in principle somehow in the laboratory. So sometimes here's a picture. What we often see is they say, well, the green set is the set of classical Bell correlations. It's a strict subset of the set of quantum correlations Q, but this is also a strict subset of the set of no signaling correlations. And similarly, as the classical correlations come from classical probability theory, and as the quantum correlations come from quantum theory, you can cook up a theory where all these non-signaling correlations come from. That's a theory that's sometimes called box world. I'll get back to that later. So these are 3 examples of a generalized probabilistic theory. So now how do we formulate such a theory and talk about it? Well, we think of a typical situation that we would want to have in our laboratories that we want to be able to describe. So we have in the beginning a preparation device. When you say press a button, then some physical system is prepared in some state. Then perhaps you do a transformation onto it. Perhaps you apply a magnetic field or something like this. And in the end, you will have a measurement. And whatever that box does is it gives you an outcome. So think of a classical coin toss, for example. You push the button and then this box shakes around and prepares maybe a fair or maybe a biased coin. What could the transformation device do? Maybe it could just rotate the coin by 180 degrees. So map heads to tails and tails to heads, for example. And the measurement device could just have a look and see, oh, is it heads or is it tails, and then flash some light. So when you think of now, what are the states in such a theory? What's actually prepared by this preparation device? Then all the statistical properties can be summarized in a vector like this. Well, you just list the probability of heads and the probability of tails. So you get P and 1 minus P. It's just a classical probability distribution. Now, what's the state space? The state space is just the set of all possible states that you could have. In this case, that's what the state space of a classical coin or classical bit looks like. Think of the center here as 1/2, 1/2 is something like a fair coin. And then the ends are perfectly biased coin. A coin that always shows heads or a coin that always shows tails, and all the mixtures in between with the different probabilities. Now, transformations, what they do is they are linear maps that map the state space onto itself. You start with a probability vector and you get another probability vector. And then measurements have outcomes, and these outcomes have probabilities. How do you compute these probabilities? Well, they must somehow depend linearly on your state. For example, you think the last device is really just looking whether it's heads or tails, and then the probability that it measures heads given the state omega is really just P. It's one of the 2 entries. And so you can think of that as a linear functional of your state that gives you this probability. So that's very simple. And quantum theory is very similar in a way. If you think of a quantum spin 1/2 particle, then your preparation device would prepare your system in a quantum state, for example, in a superposition of spin up and down, more generally in a state that's given by a density matrix. The state space would look like this. This is the famous Bloch ball for a qubit. Yeah, where if the pure states are somehow the north and the south pole and the surface, and the maximally mixed state is in the center. The transformations are now the unitary transformations, for example, or completely positive trace preserving maps if you want. They rotate the Bloch ball in some cases. And if you do a measurement, then the outcome probability of one of your outcomes of your measurement is always given by the trace rules. Your trace of some operator times your quantum state, and that's a linear functional. Yeah. So in general now, what's the general probabilistic theory? What is a state here? Well, a state is just taken as the thing that allows us to determine for all possible measurements the probabilities of all possible outcomes. That's like a catalog of probabilities. So in quantum theory, this is really the density matrix, rho. What is the state space? Well, it's just the collection of all states that a system could possibly be in. And we demand here that it's closed under statistical mixtures. So that's something Louis also talked about. What you can always think of doing is you do a random preparation. You toss a die, and if you get an even number, you prepare state omega, and if you get an odd number, you prepare state tau. And then for the statistics of all measurements that you may want to do in the future, this always behaves like 1/2 times omega plus 1/2 times tau, if the probabilities are 1/2, 1/2. Yeah. So in other words, what you have is your state space must be convex. So every 2 points in your state space, the convex combinations lying on the line between the two must also be in the state space. In quantum theory, the state space turns out to be the set of n by n Hermitian complex matrices, which have trace 1 and are positive semi-definite, the set of density matrices. Classical probability theories say for n outcomes, which just have the discrete probability vectors as the states. And in general, however, like in this picture, you can think of whatever you want. Just make up your favorite convex state space, and it describes a possible theory. What would be a transformation? Well, a transformation maps an incoming state to an outgoing state. And in order to be consistent with probability theory, you can see that it must be a linear map. In the following, we will be concerned with reversible transformations. These are transformations that you can invert. So you can compute t to the inverse to the -1. And then this is also a transformation. So in quantum theory, the transformations would be the CPTP maps, and the reversible transformations would really be the unitaries. Now, what are measurements? Well, measurements are given by a collection of linear functionals, where you say that the probability to get outcome I is just EI of omega. So a bunch of numbers that sum up to 1, total probability 1, and they are all linear in your state, and they are non-negative. So in quantum theory, this is really the positive operator valued measures. You take the trace of your state with some positive operator. All right. Now it turns out that if you have such a theory, then its physical properties depend very strongly on the shape of its state space. And I've given here an example. One is the quantum bit. Yeah, it's like a 3-dimensional ball. I've just plotted now 2 of these dimensions, like a disk. And the other one is sometimes called a G-bit. So that would be a system that has a square as its state space. Yeah. So here's a way to parameterize these state spaces. And in both cases now, we can think of a couple of measurements that we can do with systems with these state spaces. One is an X measurement. I've called the X measurement. It has 2 outcomes. And the probability, the outcomes are yes and no. The probability for getting yes just turns out to be the X coordinate of your state. And the probability for no is then 1 minus X. So this is linear in the state, and it adds up to 1. So this describes a possible measurement. And it turns out that it's a good measurement because it allows you, for example, to distinguish 2 states perfectly. Yeah, if you think of omega 1 and omega 2 for the quantum bit, yeah, probability of getting yes for omega 2 is just its X coordinate is 1, yeah, and the probability of getting yes on omega 1 is 0. So you can think of a single measurement that distinguishes perfectly these 2 states. And if you know the Bloch ball, that's what you know, that states who are antipodal on the Bloch ball, they are orthogonal, they're perfectly distinguishable. On the G bit, you can have a similar thing. You can also distinguish omega 1 and omega 2 here. In both cases, it also turns out that the maximum number of perfectly distinguishable states is 2. So there's no way to have 3 or more states that you can distinguish perfectly. So if you think of states omega 1 to omega n, and then outcome probabilities, and they are either 0 or 1 on all the states, that's the delta function that I've plotted here, then n can be at most 2. So this tells you that in both cases, you have a bit, you have a binary 2 outcome system. Yeah, but there's a big difference actually between the 2 state spaces, namely the Q bit features uncertainty relations, but the G bit does not. How do you see that here? Well, think of, for the Q bit, a state omega where the probability of yes on the X measurement is either 0 or 1. So where the outcome is deterministic. There are actually only 2 of those states, namely omega 1 and omega 2, as you can see in the picture. Now, what if I think of now the other measurement, the Y measurement, where the probabilities are given by the Y coordinate? It turns out that these probabilities are all 1/2 now. So in other words, if you can predict perfectly the outcome of the X measurement, you can say nothing about the Y measurement. It's a notion of uncertainty. But as you see in the G bit, this is not the case. So for the G bit, the state omega 2, for example, predicts deterministic outcomes for both of these measurements. And so it doesn't feature any uncertainty relations, even though it's just a bit and it doesn't allow you to read out more than 1 bit at one run. And that the shape of the state space is somehow responsible to it. Now you can think of all kinds of shapes and state spaces. A classical bit and quantum bit is what we've seen. A classical 3-level system is a triangle, for example. The classical ones would be the like the tetrahedron and so on, so the simplices. But in principle, you can have any kind of state space you want. Now you can think of a large landscape of such theories, and they all look different. Turns out like one of them, called box world, for example, has a state space where you find these super strong Popescu-Rohrlich box correlations as entangled states there. So they're really states in a theory now. And the goal now is, can you find a small set of simple physical or information theoretic principles that would pick out and single out quantum theory uniquely from this landscape of theories? The role model in some sense is special relativity. So you can think of a landscape of theories of geometry, Euclidean or Minkowski geometry, hyperbolic, or your favorite semi-Riemannian beast, whatever you want. And it turns out that 2 principles, the relativity principle and light postulate, pick out Minkowski spacetime. And it's really important to know that. And we've understood a lot about relativity by discovering this. And so the idea is perhaps we can do something similar for quantum theory and pick it out with simple principles from the landscape of all theories of probability. Right. So this now sets the stage for the second part, where I really talk about ways to do that. So the answer is yes, we can. And there are in fact many ways in which we can do this. I'll not say much about the prehistory, and other colleagues, including the Pavia group and here Czeslaw Bruckner and many other people have done that. Just mention that it's a long history to it, but there was a kind of explosion in activity started in 2001 when Lucian Hardy wrote a paper on quantum theory from 5 reasonable axioms. And that really started off this research program again. Okay, but let me maybe just now tell you how that could work. So here's an example reconstruction of quantum theory. This is due to a paper with G. Lewis, Remigijus Agusiak, and David Perez Garcia a couple of years ago. And I will now tell you 4 principles, and these 4 principles will turn out to pick out quantum theory. So here's the first postulate or principle. It's called continuous reversibility. So this says continuous reversible time evolution can in principle map every pure state to every other pure state. So why is this true for quantum theory? Well, think of a spin 1/2 particle where the state vector points somewhere. If you want to make it point somewhere else, you want to get another pure state, well, you can just continuously, unitarily rotate it over in some sense. Yeah? So unitary time evolution can always do that. It can give you every pure state from any other. And here we postulate that this should be true in general. Second principle is something that Lewis also talked about, tomographic locality or local tomography. And it says that the state of a composite system should be completely characterized by the correlations of measurements on the individual components. So think of Alice and Bob in their laboratories, and they share an unknown state psi. Yeah, maybe many copies of psi. And now they want to determine psi by tomography. What local tomography says is that they can do that just by doing local measurements and talking on the telephone. They don't have to get together in the middle and do a big, say, entangled measurement or anything. So this is true in quantum theory. And here we demand that it's true generally. It's also true classically, by the way. The third one, existence of an information unit. So what would that say? It says that there is a special type of system, the universal bit or U-bit, such that every system can be encoded into a sufficiently large number of these universal bits. Yeah, you have a system in some state, you can encode it into a bunch of bits, and then later on you can decode it again if you want. So basically what this tells you is that once you understand the bits and how they compose, then you understand everything, because everything can be embedded into that. Yeah. What we also want is that these bits talk to each other. So if two of these bits, they should be able to continuously and reversibly interact with each other. Yeah. Otherwise, there was nothing you can do. There would be no reversible transformations on two of these bits except for local ones. Now, the fourth one is one that's been mentioned many times in the past, for example, by Zeilinger, Bruckner. It says that if a universal bit is used to perfectly encode one classical bit, then it cannot simultaneously encode any, excuse me, any further information. So what does it say? Basically, it says that the U bit that we're talking about here is really a bit. It's a pure two-level system and doesn't carry 3 or like 1.5 or 2 bits. It's really a bit. And I will show you in a second how that plays out in detail. But what we prove then is the following theorem. If we have a generalized probabilistic theory that satisfies these 4 postulates, then up to linear reparametrization, the state space of n of these universal bits must be exactly that of quantum theory. So it's the set of density matrices of the 2 to the n by 2 to the n complex Hermitian matrices. And the reversal transformations must be the unitaries. So conjugation of rho by some unitary. Now, it's important to see that we have not in any way assumed the complex numbers or assumed operators here anywhere, or any kind of algebraic structure. GPTs, there's nothing you can multiply. You cannot multiply states with each other or so. You can just do convex combinations. It just so happens that these postulates are so constraining that you can derive all the structures from them. Now, let me show you a bit as an example how we can understand, for example, why universal bits must be described by ball state spaces like a Bloch ball. You only need 2 of these postulates, continuous reversibility and no simultaneous encoding. And the idea is basically the following. Continuous reversibility tells you every pure state is related to every other pure state by some reversible transformation. So if you think of the action of these reversible transformations, this is a group action. And then it's easy to see that you can always reparameterize your space such that the action of these groups are orthogonal. So they are basically rotations. So what this tells you is that all your pure states have the same norm because they are rotated by rotation. So they must lie on a unit sphere of some dimension. Yeah. Certainly, they don't have to cover the whole sphere right away. So perhaps there are holes in the sphere and some parts are missing, but they all lie on the unit sphere. Now, if you actually get the full sphere and then by convex mixtures, the full ball, then it turns out that's actually a fair, it's really a bit. You can encode 1 bit of information, for example, by preparing omega 0, omega 1, one of 2 antipodal states. But if it's not the full ball, you can do a little bit more. Yeah? Here, for example, you can encode 1 bit by either preparing omega 0 and omega 1, yeah? Or by preparing omega 0, omega 1 prime. So you have an extra choice that allows you to encode a little bit more information into your state space, and that violates no simultaneous encoding. So therefore, you must have a ball of some dimension d. Now, why is the Bloch ball now 3-dimensional? Well, right now we don't know that. Yeah, you could have a d-dimensional ball. Now let's look at pairs of such bits. If you have 2 of these bits, then, excuse me, then we know there must be some kind of composite state space, whatever it is. Yeah. And you have the local rotations on the ball. These are the local reversible transformations. They must be able to map every pure state on the ball to every other, but we don't know much more. The principle, the postulate of tomographic locality, that was one of the four here, the second one, yeah, that tells you something. It tells you what the dimension is of this global state space AB. Yeah, it tells you if you measure all local parameters, they basically determine your global state. And this tells you that the dimension of the global thing must be something like d squared plus 2d, but it doesn't tell you what that state space is. However, with quite some effort, you can prove the following theorem. So if you look at all possible dimensions and all possible groups on the ball that is transitive on the surface, then there are only two possibilities, basically. One is something like the trivial solution, where on 2 bits, the only transformations you have are independent local transformations, something like product transformations. So the bits don't talk to each other at all. And the only other case is that the ball has dimension 3, that the local group is the group of rotations, like for a qubit, and that the global thing is just 2-qubit quantum state space. So continuous reversible interaction of 2 of these balls is really only possible if you have dimension 3 and if you have standard complex 2-qubit quantum theory. And this is absolutely super not obvious. Yeah, it's really a bit of an effort to do that. And the proof is long, but if you go through it, and I'm mentioning it because I get back to that in 5 minutes, the core of the reason why dimension 3 is special here turns out to be that the rotation group in 1 dimension less, so SOD minus 1, is only non-trivial and commutative, and if D is 3. Yeah. So rotations only commute in 2 dimensions. That turns out to finally be the reason why 2 plus 1 is the correct dimension of the Bloch ball. Now, okay, so one possible loophole here is to say, well, so far we've assumed that the bits can interact pairwise, but maybe we have funny new theories where 2 bits can never interact, but if I bring 3 of them together, they suddenly have some possible interactions between them. And actually, Wojciech Dukic and Czesław Bruckner conjectured something of the sort. But 2 years ago, my student Marius and I published a paper where we showed, no, unfortunately, even if you have multipartite interaction, no new theories are possible. It's only the 3-dimensional Bloch ball that survives. Now, if you try to explain this result to journalists, then that's what they make of it. It's a bit funny here. So it says this: in a hypothetical world, quantum computers would be quote unquote boring. It's like in more than 3 spatial dimensions and with more complex bits, quantum computers would not be more powerful. It's a bit of a stretch to say what we found here, but I found it quite funny that this was the story that was made up on top of it. Okay. Good. Now, the third part that I want to talk briefly about, I think I have time, is a kind of detective story. The quest for higher order interference.
Just on time, you've got 12 minutes, including questions.
12 minutes, okay. Oh, that's good. Including questions or?
Yeah, including questions.
Let me keep this brief here. So the idea is an idea that's due to Sorkin from the 1990s, where he said, we could have, in general, more complex interference phenomena than allowed by quantum theory. So if you think of a double slit or a triple slit, and you want to compute the probability that your particle hits the screen somewhere, then in classical probability theory, the probabilities just add up. Yeah? When you think of soccer ball shooting, then the total probability of the contributions of your 3 paths, A, B, and C, is just PA plus PP plus P3. Yeah, that's written here. Whereas quantum mechanics allows to violate this, when you say quantum theory admits interference. But then here's something that classical and quantum theory satisfy. So if you look at the 3-path probability PABC, then you can decompose it into contributions from pairs of paths in the way that's written in the last line here. Basically due to the Born rule. Now you could think of general probabilistic theory and actually cook gluons where this is non-zero. So, and this would be called interference of order 3. And you can really go to the lab and try to test it. You send photons through slits, and you block some of the slits, and you see whether there's 0, and certainly so far it's 0 in on the experiments. Now here's a paper that Howard Barnum and Cosmin Udodek and I published a couple of years ago, where we again derive quantum theory, but now from other postulates. Namely, and to mention these postulates, let me introduce one terminology here, piece of terminology. Say a collection of pure states that are perfectly distinguishable. Let's call this a frame. Yeah. So in quantum theory, just pure states that are pairwise orthogonal. An orthonormal system would be a frame. But you can have it in any GPT, you can talk about this. Now here's a postulate, postulate 1. Every state can be written as a convex combination of some frame states. Yeah. So no matter what state you give me, I can always write it as a mixture of perfectly distinguishable pure states. Now that's true in quantum theory because we can diagonalize the density matrix, spectral decomposition, but here you can demand it more generally as a postulate. And the second postulate is one of a strong symmetry assumption. If you have one frame and another frame, then there should be a reversible transformation that relates the two. So in quantum theory, this is true because you have one orthonormal basis and another one, then you always find a unitary that maps one to the other. And the third postulate that came up here is that there is no third order interference. So on these triple slit experiments, you can decompose the three path probabilities into pairs of paths in the way that's written here. Now it turns out that this is very constraining. It's basically giving you quantum theory up to a couple of cousins. Yeah. It also gives you as possibilities quantum theory over the real numbers or over the quaternions. And it gives you 3-level quantum theory over octonions and the possibility of having Bloch ball state spaces, something like qubits of arbitrary dimension. Yeah. So these are known as the formerly Euclidean Jordan algebra state spaces, but never mind. But these are quantum theory and its closest cousins in a way. Yeah. Now you may imagine, well, look, isn't this fascinating? What if we have, let's try to be Sherlock Holmes here. Yeah. Let's throw away the third postulate. Let's work without it. Let's say if I only assume postulates 1 and 2, maybe then I get new theories, yeah, some novel things that nobody has ever thought before. They would describe alternative possible physics, and they would have interesting properties. So if you think of these theories, they would not satisfy postulate 3. So these would be theories that predict higher order interference in these experiments. But they have these nice properties that quantum theory has with a spectral decomposition and a lot of symmetry. And like Sherlock Holmes and Watson, we came up with like lots of properties that we know this kind of Mr. X theories must satisfy. We found out that they would have orthogonal projectors like quantum theory. The phases would give you orthomodular lattices of quantum logic. They would satisfy something called the consistent exclusivity principle. It would also be different from quantum theory in the sense that if you project a pure state, it would somehow land in a mixed state. Now the question is, do these theories exist, yes or no? Unfortunately, the answer is no. So just 2 years ago in this paper, Howard, again, now with Joachim Hilgert, proved that postulates 1 and 2 actually imply postulate 3. So there are no theories of this kind that predict higher order interference. I found this a bit disappointing. In a way, it told me that Howard is the Sherlock Holmes. He solved the case, where I was the Dr. Watson, who was hunting a Mr. X that doesn't exist. But I think it's still a nice insight that these two postulates, these very natural ones, give you directly quantum theory over a couple of different fields. All right. Now, for the last 5 minutes, I want to mention briefly something you can also see in this GPT framework, namely how quantum theory and space-time are related to each other. And I want to go back to the qubit. So in the axiomatization that I've shown you and many others, the first step you do is to prove that a bit is described by a ball state space. Yeah, a one-dimensional ball would be a classical bit, a three-dimensional one would be the usual quantum bit, could have any other dimension. And quantum theory with the reals, the quaternions and the octonions would, for example, give you Bloch balls of dimension 2, 5, and 9. And I can ask, why do we have Bloch ball dimension 3 in our world? And we've already seen an information theoretic reason. Yeah, we've seen that these 4 postulates that I've shown you enforce the dimension to be 3. But I want to show you that also kind of a space-time reason for this. with a simple thought experiment. That's here with Andy Garner and Oscar Dalston from a couple of years ago. So think of an interference experiment, something like a Mach-10 interferometer, which has an upper and a lower path. And you can think of a particle that's either up or down. So we have two possibilities. So you can think of a d-dimensional Bloch ball state space that describes where the particle is sitting. That would mean if you have a particle that's definitely sitting in the upper branch, this would correspond to the North Pole state. If it's definitely sitting in the lower branch, this would correspond to the South Pole state. And the state on the equator would give you
5 minutes with questions.
Pardon?
Just to let you know, we've got 5 minutes with questions.
Oh, sorry, yes. I'll keep it brief. Just finish this thought experiment and then I get to the end. So if it's on the equator, then we have a 50-50 probability of finding it in the upper and the lower branch. Yeah. Actually, since the probability must be linear, can work out that it must then be probability to find the particle in the upper branch must be 1/2 z plus 1. And I can ask, good, now suppose I'm sitting close to one of the arms and I want to do something to it, like put a little piece of glass inside or so. What are the transformations I can do here? Say the reversible transformations I can do in this form. Well, since it's a reversible transformation, it must somehow rotate the Bloch ball. And since you do it locally in one arm, you cannot change the probability to ending up in this arm, which tells you that the z component must be preserved. So it tells you that whatever you do in one arm or the other must correspond to a rotation of the Bloch ball with fixed z direction. That's basically the rotation of dimension d-1. Now, suppose, however, you and your friend, you fly by the experiment with a spaceship, very close to the speed of light. So you fly by, and in your frame of reference, you say, oh, actually, in this experiment, TA is happening before TB, whereas your friend might fly by and say, oh, no, TB is happening before TA. Yeah. So both your descriptions should agree on the probabilities that you get for the measurement outcomes, which tells you that these transformations must commute. Indeed, however, if all rotations of one dimension less commute, then the dimension can be at most 3, like the qubit Bloch ball of quantum theory. So you can make this a bit more formal. Let me just say this is actually the same mathematical reason that we found in information-theoretic derivation. Here it is a kind of space-time interpretation. And you can make a bit of a theorem where you actually classify the possibilities, where you say it's, if you are a bit more admissive in what you demand from your setup, you get either dimensions 1, 2, 3, or 5 for your qubit. So quaternionic quantum theory also survives as a possibility. But it's relativity of simultaneity that constrains these dimensions here to these few cases. Good. So my final slide is just to advertise some ongoing work. For the quantum Darwinism fans, so Roberto Baldiao was visiting us and he's just worked on Darwinism and general probabilistic theories. So if you find that interesting, then you can find a paper on it here. We basically say entanglement is necessary for Darwinism, but not non-locality. And with that, I want to go to the last summary slide. There are kind of lecture notes that summarize some of the ideas that you can find in the archive here. And yeah, I'll stop here. So thanks very much for your attention.
That's great. Thanks so much for the talk. Really, really interesting. Before we go to questions, just say it is quite remarkable how few things you can take in order to derive quantum theory. It's quite astonishing. Okay, if anyone's got a question, please raise your hand. Farid?
Can you hear me? Thanks, Markus, for the very, very nice talk. I really enjoyed it. So you have two main postulates in your works with Howard. One of them is the convexity, right? My question is how fundamental is this assumption? Like, what happens if we give up on convexity somehow? Do you have any intuition what we might get in that case?
So it's like, so this is basically a question about not specifically our work here, but more about the general framework of probabilistic theories. Yeah, I would say it's since like the basic fundamental thing on which you build the framework are probabilities, it's very natural to say that you should be possible to have preparations or other operations happening with a certain probability. This directly gives you convexity, but you don't have to, I think. So I would have to ask now in particular Giulio Chiribella, who has talked about this a couple of times. I think he often mentions in his talk that you can basically do everything without making this assumption. So in particular, you do not have to assume that all possible mixtures of all states can really be physically prepared, because in the end, you're only using a couple of mathematical properties. Yeah, like, oh, you want to optimize over the set here, and then it's enough to optimize over the pure states. And it doesn't matter if all mixed states in the interior are really possible or not, so you don't even need this. So you can do with less, I think.
Thank you. Thank you very much.
So thanks so much to Louisa and Markus. Really interesting talks. We've got a lunch break scheduled now. I'm going to open the breakout room again for people to keep discussing things. I'm going to ask a favor. Markus, I've got a question, and if you wouldn't mind, could you come to the breakout room, and I want to put it to you. Okay, so thanks everyone. See everyone back at 10 past. Cheers.